In this video, we'll discuss graphical differentiation. That is, if we have just the picture, the graph of a function, we want to be able to use our knowledge of differentiation to draw the picture of the derivative of that same function as a function. So let's look at a simple example to start. That is, I've drawn a little quadratic function here in red on the left-hand side. And notice I've drawn it in a usual Cartesian plane where the vertical axis is the y values and the horizontal indicate the x values. I've plotted 3 points, A, B, and C. Okay? Notice y is equal to f. So the output, the f, are the y values. And over here on the right, I've drawn another plane here where we're going to try to draw the derivative of this function. Okay, so y is the derivative of f. And this is the key thing to keep in mind whenever you're doing these kinds of problems, which is that the y value, the output, is really the derivative. Okay? And remember that derivative really means the instantaneous rate of change of the function or the slope of the tangent line at that point. Okay? And notice I've also labeled A, B, and C. So these are supposed to indicate the exact same points, A, B, and C. So let's make this graph. So the first thing to do when actually graphing the derivative of a function is to determine the slope of the tangent line at each particular point. So after you do a number of these, you'll get certainly better at this, but let's just do a quick example here. I'm going to just pick these 3 points. And this will give me an idea of what the derivative should look like, even without knowing an explicit formula for my function f. Okay? So let me draw some tangent lines here. So the first tangent line to look at is b. Right? At b, notice that the function is sort of transitioning from going down to going up. So at this point, actually, if I draw a tangent line, which looks something like this, the tangent line is flat. Okay? So that means the tangent line has a slope of 0. Okay? So that means the derivative of the function is 0 at the point B. If I look over here on this point A, here's a tangent line I've drawn right about here. Notice the tangent line has a negative slope, because if we read this from left to right, the slope is going down. And if I go over to C, which is supposed to be an equal distance away from B, in other words, A and C are equidistant away from my middle point B. If I draw a slope here, or a tangent here, I should say, tangent line, notice the slope should be about the same as it is here, if I would have drawn it more precisely. But the key is that the slope is positive, right? If I read it from left to right, it's going up, not down. So what I have here is I have the function transitioning from going down to going up at the point B. So the key thing to keep in mind here is that, in fact, the slope of this line, the slope is negative. I'll put a little negative sign here to mean it's going down. It's got a negative slope. The slope here is positive. I'll put it in little quotes for positive. And clearly you can see here that the slope of this line, this tangent line, is equal to 0. Okay? Slight abuse of notation here. So that's the slope. Okay? And without knowing the detailed numbers of what exactly the slope is, this gives me a pretty good idea of what the picture of the derivative ought to look like. Okay? So notice the key thing, again, as I mentioned before, is the y values are the actual slope values. So that means over here that, if I try a different color, the slope over here is negative. That means that the y value over on this side of the derivative of the function should be negative. I'll put a less than 0. It's negative. Okay? It's below 0. Over here, the slope, or the y value, should be equal to 0. The slope over here. And thirdly, the slope over here is positive, so that means that the y value on this side, on that graph, should be positive. Okay? And that's the key. So I'll draw the graph of the derivative of this red function in blue, where the blue indicates over here what the y values ought to be for my new graph over there. Okay? So again, without knowing any details or even knowing what f really is at all, we can certainly get an idea of what the graph ought to look like. Okay? A pretty good indication of the graph. So first of all, let me plot some points. I want to plot these 3 points. First of all, at B, the slope is 0. So that means the y value should be 0. Okay? Remember that when we're drawing the graph, and you already know this, that all the y values from the axis up, the y's are positive. Here, the y is 0 on the axis, and everything below the axis, the y's are negative. Okay? So keep that in mind. It's not always easy to transition, but these are the things you have to keep in mind. So again, when y is 0, I'm going to plot that. Y is 0 right there. When y is negative, that's over here at A. Let's just put it at some negative value. I don't know exactly what it is, but I know it's negative. Negative meaning it's got to be below the horizontal axis. And similarly, C is supposed to be an equal value, if I would have drawn this properly, on the other side, except notice that the slope is positive. So if I go to C, I'm going to kind of try to keep it about right. This should be about positive, if I would have done this properly anyway. Okay? And notice that if I want to fill in the gaps in between these 3 points, it's not so hard to see that if I were to draw more slope lines, if I drew another slope line here, for example, and so on and so on, you can see hopefully that all the slope lines from B back out negative, out this way, are all going to be negative, right? Because every time I draw a slope line, it's always going to be pointing in this direction. And as I transition from left to right, okay, from A to B, notice how the slope is going to sort of flatten out and eventually be negative. I should say negative, eventually 0, not negative. Okay? It starts off at negative, and it's going to be sort of less and less negative and eventually be 0. Okay? So the slope starts off very negative and eventually is 0. And similarly, on the other side, if I draw more slope lines, okay, if I draw another point maybe here and so on, my graph is looking a little busy now, but the point is that as I go from B out to C and beyond, the slope starts off at 0, and it goes positive, and it gets bigger and bigger and bigger. But the point is that the slope is always positive from B out to C. Okay? So I'll write that again here. So from B out to C, slope is positive. And beyond, right? The slope is always positive of the tangent line. And before this transition point, the slope is always negative. I'll put less than 0. Okay, that's the thing to keep in mind, and that's exactly what's going to happen here. And in fact, as we go from point A out to point B, it's going to change in a very linear way. Okay, so if you did this, you'll find, and if you were more careful than I'm being right now, you'll find that there's no reason to believe that it wouldn't just do exactly this. It's going to be exactly linear. So it's going to be something like this, and you connect the dots. So all you need to do is connect the dots. And we can connect the dots because we know that the red function is continuous. Okay, it's a continuous function. It's going to slowly change from one point to the next. And there's no jumps in the function at all. Okay? So because of that reason, here is the graph of the derivative. Okay? And it would continue on in a linear fashion. So notice that we start off with a quadratic function, and we reduce the power by 1. Now it's a linear function. So this is the way that we graph functions of the derivative. That is, we can take the derivative of a function graphically. So given some kind of function, even if we don't know what the explicit formula for it is, we can always draw the picture of the derivative just by knowing what derivatives do. Remember that the derivative is really the slope of the tangent line at a particular point.